Welcome back to ECE 220. Don't feel like I'm as volumed up, but maybe I am. I think the recording is fine. You do need to make sure that you are sufficiently ready to submit your pre-lab. That's due on Saturday, and that involves a fair amount of P-Spice manipulation to get all that done, and try to just be as neat as you can with the pre-lab. Make sure that it ends up all in one PDF file. And somebody was asking before class what to include in the pre-lab. I would include enough information so that if you go back and look at it in 3 weeks or 4 weeks, you sort of understand what it was that was being asked. For example, on the first one, if it asks for the color codes and you just provide as a solution 4 colors, you're going to go, well, I don't know what that means. You might say the resistor value was given as this and it has a color code structure. Or just say implies this color code band structure, something to that effect. Instead of maybe just providing the answer, you might want to give a little bit of the information behind that answer so that when you look at it in the future, you'll understand what it is that you're seeing or reading. Lab 1s begin next week. That's the purpose of turning in your pre-lab on Saturday. You'll have the different sections in Group A, E, F, G, and H for lab number 1. Homework 4 is due on Tuesday, and then Thursday is your first exam. I've been mentioning occasionally about, just linear algebra this, or now we're doing linear algebra. If you want a little background information, there is an appendix in the textbook, Appendix A, that talks about putting these linear simultaneous equations, these 3 equations and 3 unknowns, into a calculator, into MATLAB, into Excel, different ways of AX equal B and solving for X. If you have questions, let me know and we can talk about that in an office hour or some other way offline. But just know that that process of solving for X, you have different resources available to you to explain that. Now, all the mechanics behind that, they do go on a section in Appendix A on how to do it by hand. If you don't fully understand that, just make sure that by Thursday you can do a 10 by 10. No. You won't be given anything other than a calculator for your exam. You'll have your pencil, something to write with, and the exam, but you won't have any notes, so you won't be able to copy that strategy. But you should be able to solve a 2 equation, 2 unknown problem for the exam. I haven't created the exam, so I don't know if that's going to be on there, but hopefully the exam will be created by Thursday of next week. Question? Will you what?
Some of the questions were like power after a certain amount of time, like 5 seconds or whatever. I don't remember what's that part.
I think the question was, there seems to be some questions on the practice exams or the previous exams dealing with energy and power and figures and integrating possibly to find the answer or evaluating to find the power at a particular time. I'm kind of assuming that that was known information from Chapter 1, where we were talking about the definitions of voltage and current. You need to understand that. I brought in an apple trying to illustrate energy. So we were thinking about how do you find energy if you're given a power plot. Then you need to worry about integrating that power over time to find the energy consumed or supplied, depending on the question, etc. So you do want to be able to use your calculus to solve some of those problems that are associated with power and energy, current, voltage, charge, all of that. Current and charge are related relative to time, so it may be asking you something in that way as well to connect those variables or those concepts. Well, the exam number 1, the question was node and mesh analysis. I think you're asking, is that on exam 1? Not directly. So that's chapter 4, isn't it? You guys have to keep me grounded. Use one of the nodes to ground me. Have a reference potential, but exam 1 should be on chapters 1, 2, and 3. That really just sort of gets us up to analyzing or simplifying circuits with a network of resistors, but not necessarily applying mesh analysis or node voltage analysis. You should be able to do the exam problems using theory or the material in chapters 1, 2, and 3. So if you kind of work ahead, if you want to check your work, if that's possible, but it's not going to be required that you utilize node voltage analysis and mesh analysis on exam 1. Yes? Homework 4 is not going, the question was, is homework 4 on the test? No, but it's due before the test. Go figure. So we're going to have that throughout the semester. You will have to do chapter 4 material before you are going to be tested on it, but it won't be explicitly on exam number 1. So homework 4 is due prior to exam 1. That material you're going to need to be able to play with prior to exam 1, but exam 1 will focus on 1 through 3 chapter material. The question was, are we going to get an equation sheet? I'm going to have to delay the answer to that. Look at the old practice exams and see what they give you. If they say there's a formula sheet provided, then I'll stick with that. But I haven't done my homework yet. Haven't had the time to create the exam. Ask me again next week if it's not clear whether or not you get. I don't think that exam 1 really you get a formula sheet, but I could be wrong. Question.
So if the exam has a problem where we determine we could apply node voltage analysis, will we be penalized for that?
So the question was, if we want to be forward thinking and apply node voltage analysis or mesh analysis to a problem, can we do that or will we be penalized? The exam is multiple choice. I will collect, I think, your exam paper, but it will be scored maybe by a machine. That machine might be me, but I'm looking now for, is 1 C, is 1 D? So I'm not going to hold it against you if you use something in the future, which is really, we've already covered it in class. So if you're thinking that, but I think the problems are, I don't know what the problems, but I plan to have the problems in such a way that you can use your chapter 1 through 3 information to solve them. You won't need to jump ahead and use chapter 4 material. But if you do, I'm not going to hold it against you. You won't be penalized because hopefully you'll get the right answer. If you get the wrong answer, then you will be penalized. All right. Any other questions on exam? Valid questions. You need to be comfortable coming in Thursday of next week and getting ready to solve the exam. Today, what I want to do, obviously, is move ahead. We're in Chapter 4. We're in Unit 5. How else can we get you confused? Unit 5 is mesh analysis. We'll look at a super mesh example, and then the obvious question is, well, now we have 2 ways of analyzing a circuit. Which one do we use? Node voltage analysis or mesh analysis? We'll look at an example circuit. Really, it's here's the strategy. You look at a circuit and you do more than just look at it. You start thinking through how you might solve it or how it might appear to be solved based on node voltage analysis or mesh current analysis. And then after that sort of initial or preliminary thought process, you pick one and you go. But typically, you pick the one that's going to lead to the fewest number of unknown variables to solve. For example, you might have a circuit that ends up with 4 node voltages and 2 mesh currents. Well, then I would solve the one with 2 mesh currents, because once you find those unknowns, you can solve for anything else in your circuit. That's where we're headed. So we'll give you a selection strategy with little n and little m, Nevada and Michigan. If I don't enunciate correctly, you'll know maybe that I was saying N for Nevada or M for Michigan, and N for node and M for mesh. It just so happens that that's the way we can kind of keep it straight. We'll talk about a selection strategy, and then we'll get into Lab 2. Lab 1 is next week for the A group. Oh, and the A and the B has no connection with your final grade in the class. I hope you know that. Group A and Group B, those are just designations. That doesn't mean your letter grade in the class. Making sure we're clear on that. Here is a super mesh example. And the units, since I'm not labeling the different numbers, the resistors in ohms, the current sources in amperes, and the voltage sources are in volts. What we want to do in this particular problem is find the power associated with R equal to 1. And what do you expect that power to be if this is a reasonably designed problem? Consumed or supplied? Resistors consume. Now, if you built up essentially a device that you modeled as a resistor, but inside that sort of black box resistor was a lot of different circuit elements, you could build a negative resistor. But in this class, we're not going there. Okay? We're having conventional resistors, and those consume power. In this case, what would the power, well, maybe I'm getting ahead of myself, but if we now knew this voltage drop, and now I'm assuming that I've already identified a mesh current. Very first thought process, if he's already titled this super mesh, it's probably mesh current analysis. Let's now draw our meshes in the different panes of our planar circuit. And we can label these. Let me just say here's I1, I2, and I sub 3. Hopefully that's consistent with my notes. And now that I have this much labeling, what am I eventually going to write down for the power associated with resistor 1? What's my formula? And there are a lot of different formulas. I'm going to derive the ultimate one that we will use. First, we have to worry about the passive sign convention and the way that it's labeled. The way that it's labeled, power is volts times current. So it's V1 I sub 3. And now we just need to worry about the sign in front of that formula or expression based on the passive sign convention. Is it plus or minus? It's plus because we're going into the positively labeled voltage terminal before we go through the element itself with our current in the direction that we've labeled our current. But we can also use Ohm's law to rewrite V1. Let me call this R1 just so that we can say Ri. That's Ohm's law times I sub 3. Or that's now R sub 1, I sub 3 squared. So Ri squared is the power. And in this case, R1 was 1, so our formula eventually that we will use will simply be squaring the current through that resistor, since the resistor has an impedance, a resistance of 1. We okay with that? That means that we need to find I sub 3, and we've already identified in our step 1 the mesh currents. We've identified I1, I2, and I3. And now we need to start thinking about writing mesh equations. And before you get too far into it, you might say, okay, first mesh, KVL for first mesh is minus 10. Oh, there's a current source. I don't know the voltage dropped across it. So I can't write a direct KVL equation without introducing a new variable, and I've learned that I don't need to do that. Now I just need to do a super mesh. Or if that current source was not associated with more than one mesh, I would just know that, oh, that mesh current is indeed that current source, or it's negative, depending on how I'd drawn the mesh currents relative to the current source direction. In this case, that current source element is in more than one mesh. It's in 2, so now I need to think about a super mesh. So I would go up here and I'd say I'm going to bypass that current source since it's in both mesh 1 and mesh 2, and go around 2 and then bypass it again and then come back here. That's going to be my super mesh for dealing with that current source that's in both meshes. Yes? Do KVLs ever work with loops or paths like that? And the answer is yes. Is that the question?
Yeah, I mean, I know it would work around the whole outer loop because we've done that.
So now yeah, so it looks a little weird, and that's good. The question was, you're drawing things that look a little weird to me. Is that okay? And it is. KVL works around any closed path that we identify in the circuit. And that's good because we do it also with air gaps, don't we? We could, if we had a resistor hanging off here, we could find a KVL maybe around a certain path and then find what that resistance or that voltage dropped across the air gap might be. We now want to write the KVL equation for that super mesh. So let me just say KVL with the super mesh. That's now minus 10. Then we're following the red path, plus 2I sub 2, plus 2 times the current, net current going from right to left through that bottom horizontal 2. I've got a lot of 2's, don't I, resistors. What's the current in that middle resistor 2 going from right to left? Based on how I've defined my mesh currents. It's I sub 2, but we're going in the opposite direction with I sub 3. The net current through that 2 ohm horizontal resistor is I sub, going left is I sub 2 minus I sub 3. Because it's shared or in two meshes. So you're going to have two mesh currents determining that current, net current in that resistor, depending on which direction we're going. Then going down in the vertical tube resistor, what's the drop from top to bottom? Voltage. It's 2R times the net current down, I1 minus I3. And then we're back to where we started. That's now the super mesh KVL. Let me see if I can write that down. That's now minus 10 plus 2 times I sub 2 plus 2 times I sub 2 minus I sub 3 plus 2 times I sub 2 minus I sub 1, and then we were back where we started. Whoops. Keep me awake. The vertical was what? I1 minus I3. So I need to change my subscripts. You have the same answer as I do? Good. Now that we wrote a super mesh, that basically says we have to find another equation because we've basically burned two meshes with that super mesh. We need to find another relationship for these mesh currents. And how do we do that? Now we have to worry about the constraint that source presents to our mesh currents. That current source is saying, I'm going to give you 2 amps going from left to right. Well, that means that I sub 2 and I sub 1 have to abide by that 2 amps. They're constrained to always produce, going right, 2 amps. And how are they going right? Well, I1 minus I2 is the net current going right. That combination needs to equal 2. Because of the super mesh, we have a constraint equation. Because of that current source, and that says that 2 is equal to the net current going from left to right in terms of our mesh currents, and that's I1 minus I sub 2. Good. Now we have two equations relative to mesh 1 and mesh 2. Let's write KVL for mesh 3. If we start in the lower left-hand corner, we have 2. Now we want the drop going from bottom to top. That's now 2 times, what's my current? From net current going up through that 2 ohm resistor in terms of my mesh currents. I sub 3 minus I1. Then I'm going to the right to experience a voltage drop, and that's 2 times I sub 3 minus I sub 2, minus 6, and then we can't forget that resistor, horizontal resistor at the very bottom. We have a drop there as well before we get back to where we started, and that's 1 times I sub 3. That KVL for mesh 3 then says that we have 2 times I sub 3 minus I sub 1. That was going up through the vertical 2 ohm resistor. The horizontal resistor from left to right is now I sub 3 minus I sub 2 times 2. We experience actually a voltage rise, so that's a negative drop. That's minus 6. We entered the minus 6 terminal of the voltage. That comes out immediately then as minus 6 plus, just to emphasize the resistor, 1 times I sub 3, and that gives us 0. Now we're ready to solve this. And this is where I continue to say, oh, we have 3 equations in 3 unknowns. We have 3 simultaneous equations in the 3 unknowns. That's linear algebra, and that is discussed in Appendix A. Or how can I write that in a matrix form? I have these unknown mesh currents. I have 3 of those. And now this AX equal B formula or expression or equation needs to be consistent. I have a unknown set of variables, I1, I2, I3, stacked into this column, this 3 by 1 column vector or a matrix that's 3 by 1. I then need to pre-multiply that on the left by what dimension of matrix? It needs to be square, and it's 3 by 3, so that a 3 by 3 times a 3 by 1 gives me a 3 by 1 answer. What's in the 1, 1 entry of that 3 by 3 matrix? I'm going to use the first equation, the supermesh equation, to fill in the first row. Now I'm looking for the coefficient that scales or is multiplying I sub 1. I just see a 2. Is that what you guys see? This is now 2 scaling I sub 1. I sub 2, I see a 4. Somebody's out in the hallway. They're going, that guy's seeing a lot of things. He's seeing a 2. He's seeing a 4. I see a bridge. No, sorry. What's the third column in row 1? And what's on the right-hand side? All of our constants are moved to the right-hand side. We add or subtract to get them over. Let's add 10 to both sides, and that gives us a 10 on the right-hand side. Are we comfortable with where those numbers are coming from? Now the second equation says I have 1I1 and a minus I sub 2. I have no I sub 3, and those are equal to 2. I really just flipped those sides on the second equation to write that. And the third equation, I have a minus 2 scaling I1. I have a 2 scaling I sub 2. Do I have 5 scaling I sub 3? I was just seeing if you guys were even paying attention. The correction from the class said that's a minus 2 scaling I sub 2. That's correct. Thank you. What's on the right? Anything? We're adding 6 to all sides, and now we can, if we view this as A, X equaling B, then X, we just invert that A matrix and hit B on the left with A inverse. And in fact, AX equal B is really Ohm's law for this circuit. A is a matrix of resistors, X is the unknown currents, I, and B is our voltage sources that are driving the current in that circuit. Question?
I mean, I don't think you'd give us a 3 by 3 on the test, but eventually are we going to be able to use the matrix calculator?
So you will, the question was, I don't think you're going to give me a 3 by 3 on the exam. Don't go that far. You might. So you need to get comfortable putting this into a calculator and solving it. And I think most everyone here has a calculator that will do that. That's my assumption. If it's not, let me know. And I'll coach you on how to solve these 10 by 10 matrix inverses quickly. Pfft. Yeah, right. No, it just takes some time to do that. If we now solved this, we would obtain 7, 5, and 6. And before class, I plugged that into MATLAB. That's easier for me to do quickly. My calculator was slow in initializing, so I said, forget it, and just did that. So what's our final answer? P1. We were interested in the power of that 1 ohm resistor, and we said that that could be determined by Ri squared. R was 1. The I going through that resistor was I sub 3. We had the passive sign convention already employed, so now we have 36 watts consumed or absorbed by that particular resistor. Questions on that? Next example. This is now trying to get comfortable with, you're now given a circuit and not told whether to apply node voltage analysis or mesh current analysis. I may not tell you what to do. You may just have to figure it out based on the circuit. So now if we looked at this, and here's our thought process, and the units are amps, volts, and ohms. What's our thought process? Well, you might say, let me just think about node voltage analysis. If I was applying node voltage analysis, I might quickly say, I need to find my essential nodes. So let me switch colors. Are those the nodes that I would identify? And now I have maybe this one is V1, this is V2, and this is V sub 3. But V1 is connected to the reference node through a voltage source. V1 is given as 20, so that's not unknown. V2, I would obviously need to find. V sub 3, now that has a dependent source, so so I now have two unknown node voltages. I'm writing this out. You would not have to necessarily think out loud or think literally with writing this information necessarily, but you're kind of processing this as you're going. So two unknown voltages, and we have this constraint equation due to our dependent volt or current source. So we have one constraint equation from the dependent source. The idea is to do a little preliminary thinking to maybe solve the problem more efficiently at the end. That's our kind of quick thinking on node voltage analysis. What about mesh current analysis? How would we do that? Well, now we might, and how am I going to label these? Let me label this I1, this I2, and this I3. Are any of those already determined? I have a current source component, which is actually an ideal or an independent current source that is governing one of those mesh currents. I sub 2 is immediately 30. That reduces one of the variables. What else? I also have I sub 3 given, don't I? By that dependent current source. So I also have I sub 3 is now, it's in the opposite direction, but it's now minus V sub phi over 4. And that really just leaves me with one mesh equation. Now, we're trying to, so this dependent source is giving us a constraint equation. But now, what do you want to do? One mesh equation or two node voltage equations? One or two. If you're trying to get in shape, maybe you want to do the two. But if you're wanting to be efficient, maybe you want to do the one equation. So let's do mesh current analysis. Is that clear on the thought process, the thinking? So you're mentally, in your head, you're thinking through, and you don't have to do it all mentally. You can be scratching on your circuit. And you're saying, okay, what do I have? And you could even write some notes to yourself because you really don't want to mess up. So that's what I've kind of taken some notes here. And I'm saying, you know what? Let me just try the one mesh equation. If you do the two, that's fine. Especially if you do it accurately and correct. You just get the same answer, get the same results. Should be consistent. But let's now write the one mesh equation for mesh 1. Mesh 1, let's just say mesh current analysis is the winner. So that now says that mesh 1 is minus 20 plus 1 times I1 minus I2, but I2 is 30, plus 2 times I1 minus I sub 3. Let me write that down in terms of the mesh currents, and then we'll substitute or replace what we know. So we now know that this is minus 20 plus, let me get my circuit here, 1 times I1 minus I sub 2 plus 2 times I1 minus I sub 3, and then we're back to where we started. But we know that this I sub 2 was actually just given as a numerical 30, and I sub 3, that was this minus V sub phi over 4. So that this whole thing becomes 2 times I1 plus V sub phi over 4. But we can find V sub phi, that's our dependent variable, through a constraint equation. What is V sub phi? That's 2 times, now we want V sub phi to be dropping voltage from top to bottom, and then we would need to multiply that 2 times I1 minus I sub 3. V sub phi is now 2 times I1 minus I sub 3, but we just said what I sub 3 was. That was minus V sub phi over 4. And this now gives us one equation in the two variables, we can solve for I sub 1, our mesh current, in terms of, or actually we want to eliminate V sub phi in this equation so that we can solve for I sub 1. So, yes, so we're going to distribute the 2. And now we can solve that for V sub phi. We have 1/2 V sub phi is equal to 2I1, or V sub phi is equal to 4I1. And this we can now use up there. We now replace V sub phi with 4I1, so now that just becomes another I1. Or we can rewrite mesh 1 equation to end up giving us minus 20 plus I1 minus 30 plus 2I1 plus another 2I1 when we substitute or get rid of V sub phi with 4I sub 1. And that's equal to 0. Or we now have 5I1 is equal to 50. I1 is now equal to 10 amps. And if somebody wanted it, what's V sub phi? Well, that was just 4I1, so that's now 40 volts. We now have anything we need, or all the information we need to solve for whatever is asked of us relative to that circuit. We have all the currents, all the mesh currents, and we can use those however we want in order to produce the answer that's being requested. Is there maybe a little bit of a strategy for selecting node voltage or mesh current analysis? Well, here's kind of a 3-step process. Step 1, deactivate all of your independent sources. What do I mean? Set them to 0. I want to zero out my independent sources. Given a circuit, I'm trying to determine, do I do node voltage analysis or mesh current analysis? I initially just scribble on my circuit and I say, okay, I need to zero my voltage sources and zero my independent current sources. If I deactivate my voltage sources, what am I doing with a voltage source if I deactivate it? Am I taking it out of the circuit, or am I doing something else to make that voltage source have 0 volts across it? You're basically shorting that voltage source. You're replacing that voltage source with a wire. That will give you 0 voltage dropped across those two terminals of that voltage source, of that independent voltage source. If we're deactivating a voltage source, we are shorting all voltage sources. Or you're really just replacing all of your voltage sources with a wire. That's what you're doing. You're shorting it out. You're shorting across those two terminals. What if we now deactivate a current source? What does that do? Or how do we accomplish that? If we want a current source to give us 0 current flowing through it, what do we do to get zero current? Do we put a wire across it? If we short across that current source, what's going to happen? Are we going to have zero current necessarily? No, the circuit is going to give us whatever current is wanting to go through that wire, isn't it? So we're not going to zero the current through that particular connection of node A and B. What if we just remove it? Or if we put an infinite resistance, that's like removing that entire source. So now we're opening it up. So now we open up all of our current sources. Or instead of replacing with a wire, we actually remove these from the circuit. Again, this is just a preliminary step. We're not going to do this to analyze the circuit. We're just trying to figure out NVA or MCA. We'll have to put all this back together after we've made the decision. The next step in this quick process is to count the remaining essential nodes and label that N. N for nodes. So we've deactivated all of our independent sources. The dependent sources we have to leave. The independent sources we deactivate by shorting voltage sources and opening up current sources. We count the number of essential nodes. Then we count the remaining essential meshes. How many meshes are left in that circuit that's been deactivated? This is now M for mesh. Here is the final step in this strategy. We have one of these if statements. If n minus 1, n was the number of essential nodes, and we know that we fix one of those as our reference, so we really just have n minus 1 variables left. That's where the n minus 1 comes from. We're using one node for a reference node. We want to compare the number of unknown node voltages, n minus 1, to the number of unknown meshes. If we have fewer node voltages to solve for than meshes, what current should, or which analysis strategy should we use? Node voltage analysis or mesh current analysis? If you want to work fewer questions, or have fewer equations, we should do the node voltage analysis. However, if M, the number of meshes, turns out to be less than the number of unknown node voltages, then we probably ought to be thinking mesh current analysis. If they're the same, then use whatever technique, strategy you feel more comfortable using. If we have the same number of unknown mesh currents and the same number of unknown node voltages, then use whichever analysis, and here maybe this helps, requires fewer constraint equations. Maybe you do have some constraint equations, and one approach you have more than the other, maybe. Then work the one with the fewer constraint equations. That's the strategy. Let's see if we can apply that in the time remaining. Oh gosh, I'm in the exam. I have... See, there's no clock, so you don't have to be worried. But you do need to worry about the time next Thursday. But here, how would I zero this out? How would I deactivate my sources? Independent sources. How would I do that? I can get rid of that. And I can do this. What color am I? Blue, good. Now what do I have? Now how many nodes do I have? Where's my third? How many nodes? What's in? Do I have 3? How many M's do I have? What should I do? Yay! We win! Okay, so now you can do node voltage analysis on that circuit that I've erased. But you have to now put it back into play, put everything back, activate all your sources, and then analyze it using node voltage analysis with one unknown node voltage. We'll pick up next week. Don't forget, Prelab Saturday.